Hello, this is Jack Jackson. In this project, or in this video, we'll be doing a lab project where we do a z-test, where we actually collect some data. So we're going to collect data from a sample of dice rolls and use it to test the hypothesis that the mean of the sample is different from the theoretical mean for dice rolls. First, let's review the computation and parameters for the distribution of individual rolls of a standard die. Construct a table and graph for the probability density function, PDF. What are the mean, variance, standard deviation, and skewness of this distribution? Since this is something we've done before, it would be a good exercise now to pause the video and do this yourself. Come back when you think you have it done and we'll review it. Press pause now. Okay, hopefully you've done this yourself and you remember that the possible dice rolls are 1, 2, 3, 4, 5, or 6. So that's X, which is the total number of dots on the upward face of a fair die when we roll it. And since it is fair, each one of these have equal probability of occurring, 1/6 each. So when you look at the table, it's 1/6 each. That's 16.6 repeating, or about 17% for each one. And when you do the graph of the PDF, of course, it's a discrete distribution, so you get a bar graph. And each one of these is 1/6 tall, approximately 17%. Now compute the mean, variance, standard deviation, and skewness. Well, first of all, the skewness is going to be 0 because this is completely symmetric about the mean, which should be right here in the middle at 3.5. You can kind of see it visually. You can compute that, the mean and variance, from a table like this, if you remember how we did this before. So if you remember, to find the mean of a distribution that's discrete like this, we take the X value times its probability, and here they are rounded off. X times 1/6, so that's actually 1/6. 2 times 1/6 is 2/6, or 1/3, 0.3 repeating. 3 times 1/6 is a half. 4 times 1/6 is 2/3, approximately this, and so forth across here, multiplying each of these together. Then when we add those up, add up the X times the probability of X, or X times the PDF of X, we get the mean. If you add those up, you get, well, if you use the repeating decimals, you're going to get exactly 3.5. So 3.5 is exactly the mean. Because of the symmetry, that's also the median. Now, to find the variance, remember the variance is the expected value of X minus mu squared. So once we found the mu, we take the X's minus the mu's, so 1 minus 3.5, and then square that. So 1 minus 3.5 is negative 2.5. You square that, you get 6.25. 2 minus 3.5 is negative 2.5, and square that, you get 2.25. 3 minus 3.5 is negative 0.5, square that, you get 1/4, or 0.25. 4 minus 3.5 is 1/half, squared is 1/4. 5 minus 3.5 is 1.5, squared is 2.25. And 6 minus 3.5 is 3.5, squared is, 2.5 squared is 6.25. Multiply those by 1/6, and at least rounded off, you have these numbers here. Add those up, and that's the variance. Since these are all equally weighted, we could have found the mean by just adding up these 6 numbers and dividing by 6, because they're equally weighted. And similarly, we could have added up all these deviations to the mean and just divided by 6, and that would have given us the variance. So the variance is actually 2.916 with the 6 repeating, which is in fraction form 35/12. So there's the mean is 3.5, the variance is 35/12, or 2.916 with the 6 repeating. Then the standard deviation is the square root of that 35/12, the square root of the variance, or approximately 1.707285. Now we could do it that way, which is really the way you do it, or there's a shortcut we can use of sorts by using a calculator. So we can let the calculator compute this for us. So the way to do that on the calculator is you press Stat. This is for TI-84. Start by pressing Stat and then choose Edit, number 1, and you'll get something like this. First, clear your list by putting your cursor on L1, hit Clear and Enter. which will clear the list out. Repeat for list 2. Once they're both clear, put the X values in list 1, 1, 2, 3, 4, 5, 6, and in list 2, put their probabilities, which are 1, 6, 1, 6, 1, 6, all the way down. Then go to stat, well, actually quit next. So second mode would be quit. Then go to calc, stat, calc, one variable statistics. For list, use L1. For frequency, L2, which might just be on your screen as if you got an older operations dating system, it'll just look like one variable stats, L1, L2. No comma there, but there is one there. And then you'll get this screen here, which tells you X bar, the mean, is 3.5, which is not really X bar, it's actually mu, since this is an actual probability distribution. And you will get your sigma down here, which is the standard deviation to that many decimal places. And notice that you can access these variables again. Particularly, I might not want to have to type all these in again, but I can access them by hitting variables, VARS. Go down to number 5 and choose statistics. That will be sigma sub x. If I want to store that as S, I could. And here it is 1.70825,128. So we can figure that out. So we have a discrete uniform probability distribution of rolling one die. The mean, median are the same, 3.5. The variance is 35/12, or about 2.916 with the 6 repeating. The standard deviation is approximately 1.707825, which we've stored as S in the calculator. The skewness is 0 because it is a perfectly symmetric distribution. Okay, so if we roll a single fair die and let X be the number of dots on the top face, then the distribution of individual die rolls has a discrete uniform distribution with mean 3.5 and standard deviation of 1.707825, which we have stored as S in the calculator. Suppose now that we collect a sample of 60 dice rolls and record the mean of the sample. Describe the distribution of all such sample means. Describe the type of distribution, its mean, and its standard deviation. How do we know this? I'm going to leave that actually as an exercise for you to do. I'm not going to answer it in this video. You should know the answer to that based on our study of sampling distributions and the simpler limit theorem. Now, next, let's actually collect a sample of rolling some dice. Now, if you're in my on-campus class, then you will collect your data by rolling a set of 3 dice that I'll provide for you 20 times for a single total sample of size 60. If you're in an online section, then watch the video posted right after this one in the playlist to see me rolling some dice for you to use for the data for your hypothesis test. Then perform an appropriate test of hypotheses to test the mean. So you'll record your data, or if you watch the video, record it in this table here. So they'll all roll up 20 times, or you will. You'll have 3 dice, just record the first 3 that you roll here, and then roll them again, here, and so forth. Be sure you shake them up really good and roll them. Then summarize over here, these are the X's. The theoretical probabilities, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, should be close to what you get for relative frequencies here. But actually figure out what you actually have. So go through here and count all the 1s, and put how many you have here, and 2s, 3s, 4s, 5s, and 6. Divide all these by 60 to get your relative frequency here. So what do you expect to see? Well, if you're rolling 60, you expect about 1/6 of them each. So you expect about 10 on each one of these. Now, would you get that exactly? Probably not. It might be a little more, might be a little less. But collect your data, see what you get. Now perform a test of hypotheses, and you can use your calculator app for this test. It will be a one-sample z-test. Why is that appropriate? What conditions does a one-sample z-test need to be used? I want you to answer that yourself. And of course, the null hypothesis is that the mean is 3.5, which we know it should be for a dice rolls. versus our alternative hypothesis that mu is not 3.5. Perform your test. Tell me what's your p-value. What's your conclusion? Do you accept the null hypothesis? Or do you reject the null hypothesis? Are you in favor of the alternative, or do you fail to reject it? What does it say about the dice? Does it indicate further investigation is needed? If so, investigate. The next video will have me producing some data.